Okay, with today's notes, we're going to go ahead and talk about Newton's second law. But let's go ahead and remember Newton's first law. So an object at rest remains at rest, or an object in motion remains in motion at constant velocity. And I like to change this. I don't really like that term velocity here. I like to say a constant speed in a straight line. To me, that's more clear. Unless acted upon by a net external force. So there's a big implication here, and the implication is that a net external force, and remember we talked about what these words mean, okay, so net means total, external means outside, it means I can't exert a force on myself, right, some other object has to exert a force on me, and force is just a push or a pull, okay. So the implication is that a net external force causes an object to experience a change in velocity. Well, what do we consider a change in velocity? We talked about this in kinematics, and we know that a net external force causes acceleration. Okay, so that's a pretty big deal, and we're going to talk about that more now. So let's see if we can figure out Newton's second law. Okay, and Newton's second law basically links force, mass, and acceleration. And we're going to try and figure out what the relationship between those three quantities are, all right? So let's define those first. Mass is the quantity of matter an object contains. It's basically the amount of stuff, okay? We've measured mass before. We're going to measure mass in kilograms. Sometimes, like in chemistry, you'll use grams because it's a smaller unit, but we're going to mostly use kilograms. And we know mass is the amount of stuff that makes something up. So for instance, no matter where I am in the universe, my mass is always constant. It doesn't change, right? I can't change the amount of matter that's inside me. Sure, I can eat more hamburgers, but in an instant, right? I can't change my mass. I'm not going to cut a limb off, okay? Weight, on the other hand, is the force due to gravity acting on the mass. So that will greatly change depending on where I'm at in the universe. If I'm out in the middle of the outer space and I'm not near any source of gravity, my weight will be zero. My mass won't have changed, but my weight will be zero because there's no force due to gravity. The Earth, remember, the Earth exerts the force of gravity on me. So if I'm very far from the Earth and very far from any other planets or celestial bodies, there's not going to be any source of force due to gravity, so I'm not going to have any weight. Okay, so that's the difference between mass and weight. My mass is always the same no matter where I'm at in the universe. My weight will change depending on the source and the force due to gravity that's acting on my mass. Okay. Inertia is very much tied to the mass of an object. It's the tendency of an object to keep its current motion or to resist a change in motion. So inertia we define as the tendency of an object to resist changes in motion. So it resists a change in speed and it resists a change in its direction. So when we look at Newton's first law, and we said that we need a net external force for an object to either go from sitting still to moving or to changing its motion, this is what we mean. An object with a large amount of inertia, you're going to need more force to get that object to accelerate. Okay, so that's where we look at the connection between mass and inertia. Okay, so more mass means more inertia. So if you have two people standing in front of you, one is a little toddler, and one is a large linebacker for the football team, who has more mass? Obviously the linebacker. Who's going to resist a change in motion more? Obviously the linebacker. So if I apply the same force to both them and I push both the toddler and the linebacker, right, the toddler is going to have a large acceleration. He's going to go flying backwards. Whereas the large linebacker from that force won't even budge. Okay? So the linebacker has much more inertia than the toddler. So let's take a look at these two situations below. And we're going to assume that we've got people that are all able to push with a force of 20 newtons. Okay. In general, we're going to assume that the positive direction is always to the right or up. We've done this in kinematics as well. Okay. So let's take a look here, and let's see if we can figure out the net force on this crate by just this one person. Obviously, if this one person is pushing, and they're pushing to the right, the net force here is just going to be 20 newtons. Right? They're just pushing to the right, that's all there is. Okay? We're going to assume that there's no friction right here. Okay? Now, in this second situation, when we've got two people pushing, this person's pushing to the right, this person's pushing to the left. They're both pushing with 20 newtons. So those two forces are going to cancel out, and we're going to end up with a net force of 0. They cancel each other out, so we have no net force there. In the final example, we've got just one person pushing to the left, so our net force is going to be negative 20 newtons. That negative sign just means that they're pushing to the left. It doesn't mean that it's less than 0. It just means the direction is pointing to the left. Okay? So let's take a look at a couple scenarios on this next slide right here. Okay? So we've got a bunch of different scenarios. Okay? We've got, in scenario 1, we've got a pretty large crate and a pretty small person, right? So we got a pretty weak pusher here, right? In scenario B, for scenario 1, we've got a really big person, okay, with a little smaller crate here. So if I had to look at both of these and try and take a guess as to which one of these crates is going to move, I'm going to bet that crate B is going to move, okay? And the reason I think that is because it's a bigger pusher, right? So they're applying a bigger force, right? A little bit of a smaller crate as well. I don't know, maybe it's the same size. It's hard to tell. Okay. So which box will experience a greater acceleration? The one with the bigger push. Okay. When I look at this second situation, I say, okay, the pushers are the same size, but this crate is obviously much smaller in A than B. So if I had to take a guess, I would say A is much more likely to experience an acceleration because there's less mass that I'm pushing, right? So that's going to make it a lot easier for me to push that crate. So let's see if we can put those ideas together, okay? So we're going to figure out a model. We're going to figure out a mathematical model. Mathematical model just means equation or relationship, okay, between net force, mass, and acceleration. And we can see we've got 3 guesses for our acceleration. We're going to guess that acceleration is the net force times the mass. We're going to guess that the acceleration is the net force divided by the mass. And we're going to guess that the acceleration is the mass divided by the net force, okay? And we're going to use each of these 3 equations and see if we can figure out which one is correct, okay? Because we're trying to derive Newton's second law. So for this first equation, if acceleration is net force times mass, well, let's see, net force times mass, 5 kilograms times 3 newtons. This must be 15. We're not going to worry about units right now, okay? Now, if the second equation is correct, then the acceleration is going to be 3 divided by 5. Okay, and that's fine. Okay, we don't know what's right yet. And if this third equation is correct, we know the acceleration is going to be 5 divided by 3. Okay, so now, let's look at this first one. And let's see what happens when we increase the force. So now, I'm going to assume that my net force isn't 3 anymore. I'm going to assume it's 6 newtons. Let's say we doubled it, okay? Well, what's going to happen to the acceleration? I want my acceleration, if I increase my net force, I want my acceleration to go up. Let's see if it does for this first equation. So let's see. If the acceleration is the net force times the mass, well, now I get net force 6 newtons times mass of 5. I'm going to get an acceleration of 30. My acceleration did increase. That's exactly what I would expect. So this equation might be right. It's in the running. We're not sure yet, okay? Let's look at what happens over here. If the net force is 6 newtons, now my net force divided by my mass becomes 6 over 5. Okay, that's doable as well, right? This guy is still in the running because it increased just like I thought it would. Let's see about this third one. Now my acceleration becomes 5 over 6. Well, that's a decrease. So there's no way that that equation could be correct, all right? So now let's see what happens when we increase the mass. And let's say I'm going to double the mass, and I'm going to turn that into 10 kilograms. And I'm going to still leave the net force as 3 newtons that I had before. So I've got 3 times 10 is 30. That's an increase from 15. Now, does that make sense? I increased the mass, and my acceleration went up. That doesn't make any sense when we look at what we would have expected from above, right? More mass, we should get less acceleration. So I don't think that's right. So let's look at the one over here. Acceleration is net force divided by mass. So let's see. My net force is 3 newtons. My mass is 10 kilograms. So my acceleration is going to be 3 over 10. Well, that's definitely less, right? Because 3/5 is the same as 6/10. So 3/10 is less than 6/10. So my acceleration went down, which is exactly what I would have expected. So this guy right here must be our correct equation. So the equation that is going to give us acceleration, when I know net force and mass, is acceleration must be the net force divided by the mass. This right here is Newton's second law. Okay, so now we've got our correct equation, and from the last slide, it's net force divided by mass. We normally rearrange this for Newton's second law, and we say that the net force is equal to the mass times the acceleration. And how you'll normally see that written is F net is equal to M times A. Okay? So let's see some tools that are going to help us figure out how to find that net force. Because remember, net force is adding up all the forces. So it becomes very important for us to know what forces are acting on the object. Okay, so when we want to determine the net force, it's super helpful to visualize all of the forces. And we're going to use what's called a free body diagram to do that. And in a free body diagram, the object is represented by a dot. The forces act from the center of the dot. So we're going to draw arrows that are going to point away from the dot, okay? And the size of the arrow represents the force's magnitude. Magnitude is just a big word for size. I think we've used that before, okay? So let's take a look at a couple free body diagrams. So let's say we've got an apple sitting on a table. I'm going to draw the free body diagram, and I want to draw on that free body diagram all the forces that are acting on the apple. So here's my apple. I draw it as a dot. Nice and easy, right? Okay, one force that's acting on it. And I'm always going to ask, what are the non-contact forces and what are the contact forces? Because I know there's only one non-contact force, and it's the force due to gravity. And the force due to gravity is always pointing down. Okay, it's always acting towards the center of the earth, so it's always going to be acting down. That's the only non-contact force I have to worry about. Then I'm going to ask, well, what are the contact forces? And the reason I ask that is because if I know what the object is in contact with, I know what forces are going to be acting. So I know that the apple is in contact with the table. So I know the table must be providing a force. In fact, I'm pretty certain the table is pushing the apple up. If it weren't, the apple would be falling down. There's my free body diagram for an apple sitting on a table. Let's take a look at an apple falling from a tree. In this case, I know there's still gravity. That's my only non-contact force. What else is touching the apple? Well, the air is touching it, but we're generally going to ignore air resistance. There's nothing else touching the apple. So that's it. That's my free body diagram for the apple falling from the tree. Not much there, right? Let's take a look at a person pushing a box on a frictionless floor. So here's the box. I've still got the force of gravity, the only non-contact force. And the floor must be pushing up. If the floor wasn't be pushing up, then I would have a problem because there wouldn't be any reason that the box wasn't falling down. So that force that's pushing up from the floor, we're actually going to call that the normal force. And I'm going to use capital N to stand for normal. That's different than net. When I mean net force, I'm always going to write F net. Fn will mean normal force, okay? And then we know that there's a person pushing it to the right. We're going to say to the right. So I'm going to call that an applied force, okay? There's no friction, so there's no other forces drawn. That's it. That's the free body diagram. Now, if I have two people pushing a table on carpet with friction, it's going to look a little bit different. I'm still going to have my gravitational force. I'm still going to have the normal force. But I'm going to have two applied forces. I'm going to call this F applied 1, and I'm going to call it F applied 2, and I'm going to connect them like that. And I've also got a friction force that must be opposing slipping. The box would normally be slipping to the right. That friction force is going to oppose that slipping force, so I'm going to call that the force of friction. That's going to go to the left. Okay. If I have a light hanging from the ceiling, again, I'm still going to draw a little dot for the light. I'm going to have gravity acting down. Something's got to be holding that light up, and it turns out that's a tension force. So we're going to call that the force due to tension. Okay. I could put capital T there as well if I wanted to. And that's it. That's pretty much what's holding the light. I'm going to assume that the light is hanging by some kind of, it's like a chandelier or something hanging from a rope or something, or a cable, okay? Now we've got a soccer ball being kicked. Okay, there's a soccer ball, still a dot. Do you hear my dog barking in the background? Yeah, that's Daisy. All right, I've still got the force of gravity. I'm going to assume that the soccer ball is still on the ground, okay, as it's being kicked. So I've got the force of gravity going down. I've got a normal force going up, right, because the ground is still pushing it up. And I'm going to assume the person is kicking it to the right. So I'm going to put that force of kick. I could put force applied there as well, but kick is fine as well, okay? So that's the basics of how I'm going to do a free body diagram. Now, as you see here, we use the force of gravity quite a bit, right? It's pretty much always acting because we're always going to have something on the earth. And there's actually a really super easy way to figure out what the force due to gravity is. We call the force due to gravity weight. So every time you step on a scale or you put something on a scale, you're measuring the force due to gravity on that object, okay? I'm going to use, as I did above, F sub little g. It's very important that it's a capital F for force. That's how we are going to normally use our convention. And it's a lowercase g. Okay. I can always also use W. I don't like to use W for weight because we use W for something else in physics. We're going to use that for work in the next couple of units. So I think it's a great idea to just write F sub g. I understand why some students like to use W for weight because it makes you realize that the force due to gravity is the same as weight, but I'm not going to do that. That's up to you. I won't mark off for that if you do. Okay. Now the equation for the force due to gravity is a pretty simple one. I can always calculate the force due to gravity if I know an object's mass and if I remember the constant g. Remember, g is just equal to 9.8 meters per second squared. That's the acceleration due to gravity. So if I know an object's mass in kilograms, I can always find its weight because I can multiply that mass by g to find the force due to gravity on an object. All right, we're almost done here. Okay. What I'm going to ask for you to do now is complete the rest of this on your own. Okay. So this is some practice for you. The problems are pretty simple. They should look very familiar to what we've just talked about. Okay. You should be able to draw the free body diagram for number 1. I think you should be able to do number 2. We've got the 10 kilogram box, so think about what we measure in kilograms to figure out what that is. And we've got a net force of 25 newtons to the right on a frictionless surface. So I'm going to ask you to figure out what is the acceleration of that box using Newton's second law. Remember, we just derived Newton's second law above, so you should write that down here, okay? And then in this last problem, you're going to figure out how many forces are acting on a rocket when it's airborne. And then you're going to go ahead and you're going to explain why the rocket's acceleration might increase as it rises into the sky. Okay, that's a tough one, but I'm going to ask you to do that, okay? All right, that's it for today. Have a great day. Check Schoology and see what else you need to do to stay current with our class. Take care. Bye-bye.